remarkably underluminous. Its average luminosity is actually more than 8 orders of magnitude below its critical Eddington luminosity. And this emission associated with the supermassive black hole is dominated by steady emission in the radio and sub-millimeter band, and it's an order of 10 to the 36 erg per second, and occasionally Sagittarius A source associated with a black hole flares up. And when that happens, the source is also bright in infrared and X-ray part of the spectrum, and it basically reaches a comparable luminosity of 10 to the 36. But this low-level emission associated with central supermassive black hole is not the whole story, and there is also star formation activity in the galactic center. So this is a nice Chandra X-ray image of the inner 50 parsecs, central 50 parsecs of in our galaxy, which shows emission, diffuse emission, around 3 clusters: the quintuplet, arches, and the central cluster in the center of our galaxy. All 3 clusters formed young stars not so long ago, some 2 to 7 million years ago. And each of them contains about 10,000 solar masses in young stars. They are very centrally concentrated, and they comprise some of the most massive stars in our galaxy. In some cases, they have more than 100 solar masses or so. We are interested in the galactic center region, which is this region here. So let's zoom in and see what is happening in the galactic center. This is a near-infrared image of the inner parsec and the very center of our galaxy, which is marked by the cross in this image. So there are 2 colors that you can see in this image. The orangish, reddish color is actually associated with the emission from the old stars in the central parsec. These stars contribute, are actually 96% of all observed stars in the inner parsec. And when I say old, I mean they're about 1 gigayear or more in age, and they typically have masses in the range of about 1/2 to a few solar masses. Okay, but they're not the only stellar population. You can probably see the bluish emission, which is grouped around the center of our galaxy here, and this is the emission contributed by the young population of stars, the population that formed several million years ago. Those stars in the inner parsec are interesting because they appear to be confined to 2 stellar disks with different inclinations. To actually be more precise, the existence of one of these stellar disks is more solid, while the other is more putative. So there is at least 1 stellar disk, possibly 2, that contain about 100 young stars, mostly Wolf-Rayet and O-type stars, which have masses in the range of 10 to 60 solar masses and a couple of million years old. So I put this figure here to remind you that the emission that you see in this image is actually contributed only by the brightest stars in the galactic center. So what we really see is only the tip of the iceberg, because there are many more lower luminosity stars that cannot be picked up by surveys like this, just because the surveys have certain sensitivity limit and cannot possibly see all stars. But there are many, many more of those that we actually cannot see in the galactic center. And in case you were wondering what is this black square here, that is just a cutout of a particularly bright star in this region. Okay, so here's yet another way to look at the distribution of stars in the inner parsec. What I'm showing here is a figure of number of sources per arc second squared. So it's basically a number of stars projected on the sky per unit area of the sky in the galactic center as a function of radius. So this, the x-axis at the bottom, stretches from the galactic center to about 0.8 parsec or so. So I want you to first look at the red data points, which trace the distribution of all stars, or Lie-type stars. And you can see that that distribution is relatively flattish at the very center, right? And it seems to drop slightly beyond 0.5 parsecs. On the other hand, green points and cyan points trace emission or trace the distribution of young stars, so early type stars. And you can see that this distribution is quite different. These black lines are some versions of fits to these data points. But one thing that you can see, even looking at the data points themselves, is that the distribution of young stars is steeper, right? It rises steeply towards the center of the galaxy, as opposed to the flattish distributions of the old stars. The blue data points just show you the sum of both populations. Okay, so there is a difference in the distribution of old and young stars. And it's pretty striking, again, keeping in mind that we are only looking at the brightest stars. So if these stars are good tracers of lower luminosity stars that we don't see, then we have a true dichotomy in distribution of old and young stellar population. Why this happens is a little bit of a puzzle, and it's a puzzle that has been considered by many. So I will try to summarize several possible explanations proposed by a number of people who worked on this problem. So to paraphrase a suggested explanation by David Merritt and Lady Gaga, perhaps, this old stellar population was born this way. It was born with a core, or with a hole, and a deficit of old stars in the center. So some other people don't quite agree, and some of the very people in this room, including Tal, Alexander, and Pau Amaro-Seoane, proposed, or rather said, that if this old star population was born with a core in its distribution, that there are relaxation processes that come about due to the gravitational interaction of stars in this nuclear star cluster that will actually help this initial distribution of stars to relax and basically recover a cuspy distribution that is pointed at the center. And the time scales for relaxation can be much shorter than the Hubble time, and can be even shorter than 1 gigayear, basically the age of this old stellar population. Okay. Another proposition about how this deficit of old stars was created in the center is that perhaps this population of old stars did not have a core to begin with. Perhaps it was a cuspy distribution to begin with, but then at some point in the evolution of our galaxy, there was an infall of an intermediate mass black hole, which formed a gravitationally bound binary with a supermassive black hole in the center of our galaxy, and then dynamical and gravitational interaction of this binary with surrounding stars ejected some of the stars, some of these old stars, and created basically a hole or a core in their distribution. So in order for this to happen, and in order to basically eject a sufficient number of red giant stars in order to reproduce the distribution seen in observations, this intermediate mass black hole has to be a hefty one, actually. And its mass has to be about 10 to the 5 solar masses or so. This is not impossible, but at the present time, there is no evidence that there is currently such an IMBH, or that has ever been such an IMBH which since have merged with a supermassive black hole. So we don't have evidence for that scenario. Another way to do this is, instead of basically throwing in a very massive intermediate mass black hole into the galactic center, one can basically throw in several smaller intermediate mass black holes and also create a central deficit of similar magnitude. But in that case too, this has to happen on some particular time scale, so that when smaller mass, intermediate mass black holes fall in, they're able to sustain this core in the distribution of all stars, because otherwise they will slowly diffuse towards the center and recover a Casspi distribution. Okay, moving on to a slightly different explanation. One possible explanation that was put forward is that the current distribution of observed stars is a consequence of their initial mass function back at the time when this red giant and horizontal branch stars were formed. So how that works exactly? Well, the idea is that this initial mass function was particularly top-heavy, close to the supermassive black hole in the inner 0.5 parsecs. So just to remind you, the inner 0.5 parsecs is where this flattening in the distribution of all stars is seen. So this is where this deficit comes about. So what does it mean top-heavy? Well, it means that in the distribution of masses of stars that have formed at that point of time, there are some particularly heavy stars that have formed in the inner 0.5 parsecs. Those very heavy stars have very short lifetimes. They evolve quickly and basically collapse to form stellar remnants, such as neutron stars and star mass black holes, which are not particularly luminous and certainly not in the infrared. So they would not be captured by nowadays infrared surveys. So perhaps they would appear as a lack of red giant stars. The implication of this model is that somehow the initial mass function that produced this red giant and horizontal branch population of stars is actually radius dependent. So it would have to be fairly top heavy in the central 0.5 parsec, but then not so top heavy further out beyond this radius. Yet another proposed explanation is that inner half a parsec in our galaxy is a very dense stellar environment. Star-star collisions are common, and actually they are expected to happen. So if these are particularly violent, then they could damage red giant stars to the degree that makes them unobservable by current surveys. So some more recent results that are based on simulations actually suggest that star-star collisions are actually not very effective at removing this evolved stars from the inner half a parsec. As a matter of fact, quite the opposite, because if there are two main sequence stars, which later on will evolve into red giants, and they merge, they will just form a larger and brighter main sequence stars. And the same goes for red giants. If two red giant stars merge, they will just form a brighter star. So there is no way that these stars would be missed in observations. It's a slightly different story if this red giant stars, for example, encounter stellar black holes. So it's a red giant stellar black hole collision. These kinds of collisions can actually damage red giant stars pretty badly, can strip a whole lot of their envelope, or to use Melvin Davis's term, red giants can be clobbered by stellar black holes. And in order to actually remove sufficient number of red giants to match the observations, it seems that a rather uncomfortably high number of stellar black holes is needed to do that.
X-ray flux from accretion.
What about the X-ray flux from accretion?
All these black holes are
So that is correct. So if there was a particularly high number of remnants, stellar remnants, neutron stars, and stellar black holes, they would occasionally flare up in X-rays, in X-rays primarily. And indeed, there is some frequency of X-ray flaring in the galactic center, which supports the existence of or is consistent with the existence of compact remnants. But I don't know actually how much of a constraint does it put on their number. So the reason why I wanted to summarize some of these explanations is because they are all actually complex, and none of them is just a trivial answer to the question of why is there a central deficit of all stars in the galactic center. Which brings me to the most recent proposed scenario put forward by Paolo Maraseoane and Xian Chan, and that is basically an idea that collisions of red giant stars with an accretion disk and in the galactic center actually damages the red giants to a sufficient degree, strips them of their envelope, and renders them unobservable. So to be more specific, this disk in question is actually a fragmenting nuclear accretion disk, which later on will evolve to form those young stars that are observed in the stellar disk, those Wolf-Rayet O-type stars that are observed in the stellar disk in the center of our galaxy now. Okay, so the main idea here in this very nice analytic model is that red giants have very extended tenuous envelopes, and this makes them particularly vulnerable to collisions. And especially if red giants collide with a fragmentic disk, which later on forms a disk of stars, in that case, red giants can really lose a significant fraction of their mass, perhaps some 50% of the mass. And indeed, the prediction of this analytic model is that red giants with radii of about 150 solar radii can lose order of 50% of their mass if they collide 10 times or thereabout with clumps of surface density, clumps that live in this small nuclear accretion disk with surface density of 10 to the 4 grams per centimeter squared. I also wanted to mention that there is one numerical study that looked at star disk collisions. It was done in 1996, almost 20 years ago, by Armitage, Zurich, and Davis, and the sequence of snapshots from their SPH simulation shows you basically, or illustrates rather, a collision of a star with a disk, and the fact that star loses good amount of mass and is deformed in these collisions. In this study, Armitage et al. Actually did not look into star disk collisions in the context of galactic center. They were after a different question. They actually wanted to see whether the mass stripped from red giants and supplied then to the accretion disk is sufficient to basically power active galactic nuclei. So that was the question that they studied. But both of these studies arrive at consistent conclusions that in these collisions, indeed, red giants can lose a good fraction of their envelope. And that mass can, to some degree, power active galactic nuclei and can also render red giants invisible. Okay. But it's worth mentioning, however, that this missing population of old stars in the galactic center is actually well represented by garden variety red giant and horizontal branch stars, which are actually a little bit more compact. So to illustrate this, I'm showing a figure, or two figures rather, illustrating post-main sequence stellar evolution that was calculated with the code MESA. And it was calculated by Morgan McLeod et al. And what is shown is actually a radius of a star as a function of its age. So you can see what is basically the radius of the star as it evolves from main sequence to red giant branch, horizontal branch, asymptotic giant branch, and all the way to the white dwarf stage. So the top panel shows you the evolution of a star which initially had mass of 1.5 solar masses. And just to remind you again, the masses of all stellar population that is seen in galactic center are somewhere in the range of 1/2 to about few solar masses. So these two masses belong to that range. So you can see that the radius that this star would have during its red giant evolutionary phase would be, on average, about 10 solar radii, and it would retain that radius for several 100 million years. If the star started a little bit more massive, closer to three solar masses, it would evolve through the red giant phase really briefly, but it would spend a little bit more time on horizontal branch, about 100 million years. And during that time, it would also have a radius of about 10 or 20 solar radii or so. So why does this matter? Why does it matter how big the star is? Well, it is important because more compact stars are more resilient to collisions. So in order for them to lose a significant fraction of their mass, they either need to have more impacts with clumps, or they need to encounter denser clumps. Okay, well, in that case, one may wonder whether this model is still a plausible hypothesis for explanation of the central deficit of stars, because it's harder to hit smaller clumps, so it will take stars a little bit longer to encounter these clumps, if they have to have more impacts, then also some time scale that should happen on a time scale that is shorter than the lifetime of a red giant star and shorter than the lifetime of a clump, and so on. So we decided to test this hypothesis by carrying out hydrodynamic simulations of star disk collisions and either confirm the model or keep Pau's fit to the fire. Okay, so what is the computational setup of our hydro simulations, which were carried out with a grid-based code? Well, the basic idea for the setup is that there is this nuclear accretion disk. It fragmented at some point, and it formed Wolf-Rayet and O-type stars later on. Its size is somewhere in the range of 0.0 few to about 0.5 parsecs. This is constrained by observations. And we are considering red giant stars that are orbiting around and perhaps have 1 to 2 encounters with this fragmenting disk over their orbit. We are not modeling the entire disk in our simulations. Rather, we use computational domain, which is centered on the red giant star, so we keep it at the center at all times. And then we have the ambient medium fly by. So basically, we have the clump fly by the star. So this is a 3D visualization of our computational domain, which is 4 by 4 stellar radii on the side. Those red giants that are orbiting in the inner half parsec have orbital periods in the range of 10 to the 3 to 10 to the 4 years. And they have orbital velocities somewhere in the range of several hundred to perhaps 1,000 or 2,000 kilometers per second. So this is the range that we considered in our models. We considered red giant and horizontal branch stars, or model stars with radius of 10 solar radii, with some characteristic mass of about 1 solar mass. And such stars have dynamical timescale of about 11 hours, which is very similar actually to the sound crossing timescale of the star. And since it's the shortest timescale in our problem, we use it as a natural time unit. So I'm showing here a density distribution for 2 stellar models that we consider. We model our stars as polytropes and consider 2 polytropic indices. The solid line here shows the density profile over a stellar radius for gamma equals 1 polytrope, which is typically used to model lower mass stars. And the other line marks the polytropic model with gamma equals 4/3 index, which is usually used to model more massive and more evolved stars. How much time do you have? 20. Good. Okay, so the reason why it's more often used to model evolved and more massive stars is that these stars have a distinct core, which is almost separate from their very tenuous outer envelope. So I basically indicated here with an arrow that if you actually look what's happening beyond 0.5 stellar radius, there is barely any mass there. So you can right away expect that the envelope is very easy to strip from these stars, but that there is not a whole lot of mass in it. Another way to look at the same property is actually to plot the surface density. So this is a projected density, column density of the star in units of grams per centimeter squared, again as a function of radius. So again, solid line shows the gamma equals 5/3 polytrope, and the dashed line here shows the other model, gamma equals 4/3, and this little blip is just a numerical artifact, so feel free to ignore it. So why is this useful? Well, this visualization is actually useful because if you plot the density of the medium that the star encounters, you can right away see which portion of the stellar envelope will be lost. So for example, if you immerse a star or let it collide with a smooth accretion disk, which is not fragmenting, such a disk would have surface density of the order of 10 to the 3 grams per centimeter cubed. And you can see that the region where it intersects the star is pretty much its outer radius. So in this case, if a star collides with such a disk, it would escape pretty much unscathed because of the low density of the disk, so it won't lose any appreciable amount of mass. On the other hand, if you have a red giant star collide with a clumpy disk that is fragmenting and therefore has higher density pieces in it, densities would need to be in excess of 10 to the 7 grams per centimeter squared in order to actually remove appreciable amount of the star's envelope. So if you, for example, look at the dashed density profile here, the point where the blue line, which is at 10 to the 7 grams per centimeter cube, intersects this profile, tells you that the envelope beyond the 0.8, 80% of the stellar radius will be removed in this collision. Okay, so motivated by this, we then simulate collisions with clumps, which actually have surface densities which are of order of 10 to the 7 and 10 to the 8 grams per centimeter squared. So they are quite dense, and they have sizes corresponding to 10 to the 13 or 10 to the 14 centimeters. We assume, following Pao and Xian Chen's work, that these clumps should have mass of at least 100 solar masses, and the idea is that these clumps eventually have to evolve to form Wolf-Rayet and O-type stars, and therefore they have to start massive enough in order to be able to form 10 to 60 solar mass star. Their lifetime, the lifetime of a clump, can be estimated to be about 1 gigayear, and that is assuming that the clumps are collapsing and releasing their gravitational potential energy, emitting as black bodies, so it takes them a long time. And just as a comparison, a clump crossing timescales are actually very short. They're about 5 to 100 dynamical times. You remember I told you dynamical time is about 11 hours for this type of stars. So the clump crossing is relatively rapid, but it depends on the velocity of the star and size of the clump. I'll tell you later, yes. So, or in a moment, not so much later. So we consider two setups. A continuous setup, where star basically just enters a dense medium, which is supposed to model a clump, and then keeps traveling through the dense medium. So it's almost like having clumps back to back together, and the star keeps traveling through them. And then we looked at the importance of repeated impacts in scenarios where star just keeps impacting discrete slabs of gas to see whether this makes any difference to the mass loss. So these are the two plots that show the mass loss from the star in the continuous setup. So it's basically swimming through this high density medium. And the left plot shows collisions with clumps of surface density 10 to the 7. The right plot shows collisions with denser clumps, 10 to the 8 grams per centimeter cubed, and as a function of time, in dynamical times. Different lines here show the orbital velocity of the star. So this is basically collision velocity between the star and the clump, and not surprisingly you can see that star tends to lose more mass if it moves at high velocity. And in the left graph you can see that the star basically loses about 1% of its mass during 100 dynamical times.
How do you readjust the stellar structure as the mass goes down? Is
With lower mass and larger radius. I'm not sure what you mean.
He's asking you to solve the polytrope equation.
Yes.
Radius, right? So
Yes.
radius is the less for a pure polytrope, right?
Yeah.
The less mass they have.
So we start the stars as polytropes. We solve the Lane-Emden equation and then just let them evolve. Basically, we create a density distribution and let them evolve in this background medium.
I think what he's saying is after an impact, there's basically entropy injected in the envelope.
Yeah.
You have removed, so then, if you map it into stellar evolution, the star after one collision is actually going to.
Oh yeah. So we don't stop the code. So the star basically evolves through multiple encounters. So therefore, whatever entropy it gains, it is evolved self-consistently. Okay. So encounters with lower density or lower surface density clumps will give a mass loss of the order of 1%. Well, how about the denser clump? Well, for a denser clump, this same orbital velocities of the stars actually give a substantial mass loss, basically of order of 10 or 20% or so. Okay, so these types of collisions can indeed remove a substantial fraction of mass from the star and perhaps render it unobservable. Just to translate this time scale of about 100 dynamical times to the number of impacts, you can see that it corresponds to about 10 impacts or so. One can also plot this mass loss as a function of orbital velocity or collision velocity. And we did that for both densities of the clump. This is the lower density clumps. This is the higher density, 10 to the 8 grams per centimeter squared. And just for numerical facility, we actually fit a line, straight line through it. Although, to be honest, entirely honest, this is not a straight line. And there is some rolling index to this mass loss as a function of stellar velocity. But it is something that could be used in analytic calculations. And of course, for stars which are modeled as polytropes gamma equals 4/3, the mass loss is even less. So this is basically an upper limit on the mass loss that we find. We then looked at the effect of repeated impacts. What I'm showing in these two figures is a particular scenario, 10 to the 8 grams per centimeter squared for clump surface density, orbital velocity of the star of 6,600 kilometers per second. So in the left plot, you can see the mass of the star as a function of time. And every time you see this step, basically, that is when an encounter with a clump happens. So the star is traveling through the clump, where mass is dropping more rapidly, and it spends about 20 dynamical times outside of the clump. We, of course, did not want to model half an orbital period because it would take a long time to follow the star as it travels through a low-density interstellar matter, which is not so important because star doesn't lose any mass during these intermediate times between clump collisions. We also measure the linear momentum of the star, and we track the kinetic energy of the star. And that's one way to track the efficiency of these collisions. Basically, stars will slow down due to these collisions. And we find that repeated impacts are actually more efficient at removing the red giant envelope than the continuous tunneling of a star through a clump. And they lower linear momentum and kinetic energy more, and the mass loss in the end is more. One way to basically measure this is to measure this index F, which is just a simple ratio of the mass loss for collision n number 1 divided by the mass loss during the collision number n. The reason why this simple index is useful is because, again, it's used in analytic models so to account for this type of mass loss. So we measured that factor for repeated impacts and found it to be a little bit higher, about 10% higher on average than for the continuum model. However, this is per impact pretty much. So after many impacts, this mass loss, difference in mass loss actually tends to build up. And another thing that I want to point out is that based on previous numerical studies, the expectations were that this factor was closer to 2. So we really find it to be a good bit smaller than that. It's actually asymptotic to 1. So in the end, can star-disk collisions explain the missing red giants in the galactic center? Well, just to recap what we learned from simulations, red giant and horizontal branch stars with this radius that have been removed from the population of observed stars must collide with clumps about 10 times in order to lose a significant fraction of their mass. These clumps have to be compact, and basically their surface density has to be in excess of 10 to the 7 grams per centimeter squared, which right away puts a constraint on their size. So they must be small. So one can use that information to calculate the rate of collisions based on purely geometric arguments, basically by dividing the cross-section of clumps by the cross-section of this nuclear accretion disk, multiplying by the number of clumps in the disk, dividing by the orbital period of red giant stars with semi-major axis A, and multiplying by a factor of 2 just to account for the fact that during one orbital period, star can collide with a fragmenting disk twice. So this was nicely laid out in Pau's analytic model. So one can basically take the inverse of that in order to calculate the average time between collisions. And we did that and found actually somewhat dishearteningly large value, 20 billion years, which is longer than the Hubble time and longer than the age of these red giant stars and the lifetime of a clump. So this is a bit worrisome, but let's see what kind of assumptions go into this kind of estimate. First, there is a number of clumps, and we use the number of 100 here, which is simply motivated by the fact that the number of young Wolf-Rayet and O-type stars seen in the galactic center is about 100. But there is nothing to say that initially there was no higher number, even higher number of clumps in the galactic center. Perhaps some of them were disrupted, some of them collided with other clumps to make even more massive clumps, and so on. So this number is actually a lower limit on the number of clumps that such a disk must have had. This is just the radius of the nuclear stellar disk. This is the radius of the clump constrained by our simulations, and this is the same major axis of the red giant stars. So there is one more hidden assumption in this simple estimate, and that is that the orbit of a red giant is impacting the disk perpendicularly. So the orbit is perpendicular to this nuclear accretion disk, but it may just as well happen that the orbit of the star is actually aligned to some degree with the nuclear stellar disk. So instead of just impacting perpendicularly, it actually has a longer mean-free path through the disk, which it means that it can encounter more clumps. And as a matter of fact, it can account up to 30 more. You can have up to 30 more collisions or thereabout if the star is co-rotating in the disk. So these two factors, a larger number of clumps and a coplanar orbit, can in principle shorten the average collision time by several orders of magnitude. But it's uncertain by how much exactly. So if this collision timescale can be as short as 10 to the 7 years, then there would still be enough time for red giants and horizontal branch stars to collide tens of times with these stellar clumps. So even though this uncertainty range is rather uncomfortably wide, several orders of magnitude, it is not impossible that actually star-disk collisions can account for the deficit of the old stars in the galactic center. So the model passes the scrutiny of at least this set of simulations. So thanks. So the stellar disk has a mass of about 10 to the 4 solar masses, the observed stellar disk in the galactic center, which means that it had at least that much mass, but probably much more at the very beginning, because when these massive stars form, Wolf-Rayet and O-type stars, they actually tend to lose a lot of their mass to stellar winds. So it's quite likely that the disk was more massive, maybe 10 to the 5 solar masses. But
And so you can actually get this model to work better if you have greater density?
so higher surface density in the clumps definitely helps. But on the other hand, it also means that, so we are basically starting with a fixed pool. We are starting with a disk of mass of 10 to the 4 solar masses, forming 100 clumps, 100 solar masses each. And then they're collapsing. So that means that the higher density is the clump, the easier it is to strip the stellar envelope, but it's harder to hit the clump because it's more compact. So there is a trade-off in probability versus stripping efficiency.
And you model the disk is uniformly dense?
So we don't even model the disk, we only model the star that is traveling through some dense ambient medium, but the implicit assumption is that the disk is populated by the clumps of the same size and same mass, because we only considered clumps with these properties, 100 solar mass and this particular size.
One of the things I was just thinking when you were trying to increase the number of collisions, you have 100 clumps, but if you look at what happens to a clump after you collide, how much energy do you make to the clump when you pass it?
Yeah, so not a whole lot. That kind of estimate was already done by Pau analytically, and we also see it numerically. The star only deposits a tiny fraction of energy relative to the gravitational potential energy of the clump itself. So it's not going to destroy it.
So to make the model more efficient, you say it's better to have the star almost aligned with the disk, right?
Or yeah, hitting it obliquely, right? Because it has a longer mean free path through the.
But the more you go in that direction, the less the delta V is going to be, and I guess each collision is going to be less effective.
That's an interesting point. Unless they're counter-rotating or something. Yeah.
Yeah, or fewer elliptical.
Well, even on eccentric orbits, delta V would be smaller, right? Because if they are co-rotating. Yeah.
So it must be like maybe one can estimate what's the maximum effect that you got into account.
Mm-hmm.
You really care about the escape velocity from the very tenuous and extended envelope and the mean velocity against the medium you're colliding with.
Yeah.
I think that those radii, typical of the velocity dispersion, if it's of the order of the velocity, circular velocity, would be well above the escape velocity from the envelope. So you'd be losing mass even if you are chasing the cloud in the same direction.
Mm-hmm.
Yeah, this is totally independent from.
Yes.
I mean, going back
Yeah.
to the comment that you made, I think it's very important because after you have one first passage,
Mm-hmm.
the second passage is going to take a long time, and the Kelvin-Helmholtz time scale of the envelope is hundreds of thousands of years, and the star is actually going to readjust its structure, before the second passage comes.
Yeah.
So something that you may want to do is basically map the star when it comes out of the clump into massa, let it readjust it, and then
Oh.
re-inject that into
Right. Let it settle down. Right. So that would perhaps mean that for this
It may actually help.
repeated.
Yeah, because basically you increase the cross section.
We actually see a little bit of that phenomenon. We don't relax stars on such long timescales, but what we see, maybe, I don't know if you can see it in this figure, is that once the star exits the clump, so this is the model of repeated impacts, so the star leaves the clump, but then its stellar envelope swells up. Once it exits into the very low density medium, its envelope sort of is extended, which is why we see that these repeated impacts are actually more efficient at removing mass.
The time scale between your time scales is only 10 dynamical times.
Yes, it's short, but even for that very short time scale, we see a little bit of that effect.
I mean, it may be also another limit, which is that, we do
Mhm.
star actually becomes extremely limitless for a very brief period of time. And the question is, can you have, is there any hope of actually finding the remnant of the star that actually just interacted with the disk and it became, significantly bright? What's the number density of sort of
Yeah, those are squeezers, if I remember correctly, named by somebody who I'm not going to call.
Well,
A
a little bit more aggressive.
little bit more aggressive than squeezers. Yeah.
It's just exposing the stored heat under the envelope. It's not a squeezer. It's simply basically like taking away the stuff that was stopping the photons from diffusing very quickly and allowing all the internal heat in the new photosphere to just fly away. That would be the flash rate described. So it would be very short, of course.
Yeah, you can calculate like how many, what's the diffusion time across your envelope, and that will tell you the time scale for that heat to leave.
Mm-hmm.
So,
Mm-hmm.
A similar question to you. Can you make more clumps by when the red giant crosses the non-clumpy regions of the disk? Can you make it? It's an unstable disk where most of the passages are not through clumps, right? Through the normal background disk.
Mm-hmm.
Can that make more clumps by storing them?
Yeah, we didn't try.
Has anybody actually simulated the disk itself?
So I think that have you actually simulated this fragmenting disk, and have you ever tried to perturb the smooth disk rather than let it fragment by itself and see what happens? So Zoltan is asking if you actually add additional perturbation to a fragmenting disk, would you fragment more, I guess?
It's prone to fragment.
Well, not quite, yeah.
It's an
There's
unstable
a
disk.
recent paper by Hosanna and Edwin on that, like if you have a fragment forming somewhere, you have different cooling times in the disk and so on. You have one fragment here and you will drive fragmentation further in. But whether collisions can do that, I don't think anybody.
Because there are a lot of collisions.
yeah, like
True.
what the heating rate of the disk and how does that compare to the standard viscosity is probably just a small perturbation.
Sure, but one thing to keep in mind is that you are starting from a fixed reservoir of gas. So maybe you can create more clumps, but they will be smaller. So yeah, there is a trade-off, again, with probability to encounter such a clump versus...
Very basic question. Just how many clumps can you make maximum? What's the mass of the clumps? You get 100 clumps.
and each has mass, so about 100 solar masses, and this is basically motivated by the mass of the stellar disk that is observed in the galactic center, which is a order of 10 to the 4 solar masses. So the disk could have been more massive to begin with, but yeah, this is a lower limit on the mass.
For the purpose of losing angular momentum and driving the stars to the rock to the orbit of the disk, can you remind me the numbers? If you multiply the amount of collisions with the mass that the star kind of pushes out in a
Right.
how much mass does the star encounter during these hundreds of collisions? Is it equal, roughly equal the same amount to its own mass? That is what would be required in order to
You saw it's only getting to the edges, so in 100 it's basically
no,
going to
it
collect.
loses the edges, but the effect is throughout the interaction.
Yeah, if you multiply the column density that she had by the size of the object,
Yes,
multiply by 100, it's almost like a few percent of the mass.
Yeah, it's not comparable.
The stars would actually be driven to the plane of the ring.
So we are modeling on order of 10 collisions. So in 10 collisions or so, the stars are not going to be dragged into the plane of the disk. If they're interacting for many more orbits or many more collisions, then it could become a factor.
I mean, if you have a quasar occurring at the Eddington ring, probably there you can drive the stars.
I think that was studied by a number of authors, and they actually show that stellar orbits, after many orbits, can be dragged into the plane of the disk.
Many of these things, at least after order of unity, different
Mm-hmm.
uncertainty can be estimated from just, back of the envelope. And I'm wondering
Sure.
to what extent if you either show or disprove that
Mm-hmm.
If you send to the profile,
The Mesa calculation to readjust the evolution of the star. Yeah, so we didn't model the star for 100,000 years in order to see how it readjusts in this case. It was just too long of a time scale. But on the time scale that we did model, we do see the expansion of the envelope by a little bit.
So you use similar numbers to those that we use, and you get similar results. And actually, this geometrical factor over 10, whatever,
Mm-hmm.
we're also assuming 1, 1.1,
Mm-hmm.
and we got something like a unique 30 impact, something like that.
Yes. Of order of 10, right. Yes, I'm happy to.
okay. A happy note. Let's thank all the speakers again. So we'll break for coffee, half an hour, and then we're going to explain what's going to happen. So we meet everyone back here in half an hour.
Yeah. So this part of the group can go to the first floor. There is a big room in the first floor.
Are you listening? Everyone listen. The right-hand side will go to the first floor, to the large group, and the second part will stay. That's very nice. We have a little subroutine in Mesa. You did this with Flash, or what code did you use?
It's a relatively anonymous code that
Okay.
is based on VH1, which was
Okay.
Chime working with me, basically.
So if you do like equal entropy surfaces and just do your integral and send a 1D profile, then Mesa will read it and then evolve it and then gives you an output.
Right.
So if you're interested in that, we can send you the code to do that, or we can do it ourselves. If you want.
Right. So I believe Morgan has done something similar with Red Giant.
So in this case, because it's only one encounter, we haven't really, well, so now we have done it for main sequence stars, in which, James broke the main sequence star, but then you have all the spiral waves and the material falling back, so the star actually grows quite a bit, and then we tried to calculate, we call them facelifting of stars, because you can make them look younger. And we wanted to calculate what's the time scale that the star looks hot and different, because also if you get the kick, we wanted to see if you can see them within the galactic center, but their lifetime is very short.
Yeah. Although the scenario is slightly different in that case because that star is tidal massaged a little bit more. So
It's probably more aggressive than here.
This is all surface basically before.
Yeah, so Morgan did it in the case of the multi-passages. And in that case, we did use we started removing mass slowly and let it readjust with Mesa. But in that case, we didn't really resolve the hydrodynamical violence that you have, which is really the shock and the Kelvin-Helmholtz and stabilities and all that beautiful structure.
So I'll think about it because the relevant timescale is actually the timescale for the relaxation of the envelope, which given the low density has a higher speed of sound.
Yeah, so
We adjust a little bit faster than before.
yeah, so Morgan had in his, I think in the face, I don't know how to call it, the spoon feeding paper. After the snapshot, he has a snapshot in which he calculates the diffusion time from the resultant star. And you just basically calculate the density and, with the Thomson cross-section, what the diffusion time scale would be. So if you take a snapshot of at the end of your first passage simulation, then you can, you can get a feeling of how long it will take for that heat to basically, leave the envelope. And if that is 100 years, maybe it doesn't matter as much as we think it matters. But if it's 10 to the 4 or 10 to the 5, you may have to.
I'll check it out. I thought I calculated that, but I don't know.
And then the other thing that we find in the tidal disruption case is that the core actually protects the star, Because as you try to strip the envelope, the core gravity tries to protect it. So I don't know if you put a point mass.
We don't have a point mass. But we never really burn off half of the star more than that.
And you have self-gravity of the star?
Yeah, the star is small. Yeah, the star is.
And you have some, like the multiple
Right.
expansion. Yeah, that's very nice simulations.
It was a simple setup. History is actually done mechanically using undergrad, so it seemed like a nice project.
Yeah, that's very nice. I'm a little surprised of the sizes of your clouds. They're only 10 to the 14 centimeters. They seem very small.
So that is what comes out if you just calculate basically the size of clumps, which are pressure supported against gravity. And,
Because the size of like the cores of molecular clouds are only like 10 to minus 3 parsecs.
Okay. So this is 10 to the 13.
So this is like 2 orders of magnitude smaller. Do we actually see any
10
observations?
to the 13, 10 to the 14. So our densest clumps are of order of a few times 10 to the 13. Our lower density clumps are order 10 to the 14.
I see.
So
Do actually we have observations in the disk or anywhere that clumps that compact exist?
I'm not aware of it, because we don't see clumps in that. I think that what they detect those, depending on what you think about the G1, that's probably not. But in this stellar disk, I don't think that
They see such. So you're thinking really where they're basically about to form stars and they're just collapsing?
That's almost a star.
Mm-hmm.
By the time you're next to the surface, that's not really. Because if you think about it, it's just the radius of the square is much larger than
Yes, the star, yeah. Well, they're giants. And I don't know, when you enter into the Hayashi cloud, where we see the stars, they are much thinner. No? They're sort of the sizes initially in the Hayashi track are like 10 to 14 to 15 as they cool and get into the main sequence.
Yeah. So I guess the difference is that we just found our clumps as uniquely dense clumps. So they don't have pores.
Yeah. I wonder if you take like a really power density spectrum of the ISM, what is the characteristic scales of this?
Yeah. We know that there are 10 clouds.
Yeah, I think that the ones that I remember are like were for clusters of stars formation. What people use, or even for very massive stars, they use the cores of molecular clouds. And I remember the cores of molecular clouds are like 10 to minus 3 parsecs, maybe like 10 to the 4, 10 to the 5 particles of the CC. And those they see them in CO.
They're 10 to the 4, 10 to the 5 grams per centimeter square.
No, particles per CC.
Particles per centimeter cube.
Yeah, so they're about maybe 10,000, 100,000 times more denser than the ISM. But of course, like, the ones that you're calculating are really now. I don't know if they were already in the free fall.
It used to be you want to have molecular clouds.
No, I was just saying that I don't know if in the ISM we have evidence for something that is that compact and that massive.
And longer that would be recognized.
I-
Molecules would be associated with something just because of the temperature. Becomes
Very nice. I enjoyed it.
Copy?
I have lots of stupid questions. Can you, this dynamic of friction, can you just move the young stars in as opposed to move the old stars out? Or is that, can you move
Like
the,
some mass aggregation.
yeah, just so much. Probably that answer is good. Massive stars is also usually potential. Can you just,
Well, you can find that in stellar visions right now. And then
I think some of the figures that you mentioned at the beginning when they tried to mass segregate, I think what they tried, but I think the time was probably not possible.
Yeah, I think it's for sure that the testing is quite simple.
actually, if you actually make them go into the plane, I never thought about this. I don't know if you've seen any papers. So when you solve stellar evolution, your outer boundary is basically a zero pressure boundary. But if you're inside of this, then you have a very large pressure outer boundary, and you may actually get heat conduction inside the star. And I wonder if this could actually be stellar evolution.
So that's interesting. I remember a suggestion by, who was that? It was, Red Shields, some time ago, that if the star is a white dwarf, in principle, you could certainly have
Or become a giant.
a super electron. Just inefficient.
Pal, do you know if anyone has thought about if you're able to move stars into the plane of the disk? Yeah, and then the star is sort of coplanar with the disk. When you try to solve the equations of stellar evolution, you usually use a zero pressure boundary in the outer parts, but here you don't, and you can have actually quite a hot disk. So maybe stellar evolution will change because then you have a huge amount of heat transport in the outer parts.
Maybe some people have looked into that for the Galactic Center where you can have some gas here and there, unfortunately, maybe, or manage some.
I've thought about
Sergey.
Yeah, that's interesting. I know that people have definitely worked in stars with way solution disks, but I'm not aware of that for specific star structure.
I will try to see if you may change the outer boundary conditions in NASA and try to evolve them.
Yeah. Because you do definitely confine the star. We see less mass loss from stars that are having continuous movement as opposed to having repeated impacts. So the low shock protects the star as well as the pressure.
I'm gonna get some coffee.
When you run it through
Pamela, do you want some coffee? Or I can bring if you guys want to continue your talk.
I'll just actually got a cup of water. What do you join? Are you staying here or are you staying here?
You have to move, Sultan, just to get the hot coffee.
Otherwise,
3 and 4. What's that page?
Hopefully my questions on page 3 and 4, because they were the best ones, I'm sure.
Yes.
Yes, they are. All of them, yes, they work best.
Well, I've done these enough. Although I do want to find someplace I can hook my foot on.
I thought the people would come back here to see this.
Well, we have to know where we're going. But yeah, people are starting to come back.
Okay, they are already on the ICT webpage as well. So I go to floor 1, I'm group B then.
Lead us.
Okay. So do we need to set up anything else? No.
Somebody else does
Sure. Look on Friday.
Sure. Well, I keep thinking the days.
So the only one thing, on Friday, we cannot keep in room, on Friday afternoon, but I will sort it out. I won't tell anything to anybody. Just right, the day before. Yeah, just avoid to take the metro between 5 and 7. Unless you want to actually go to cameras. Right, so if you want to leave, but no, you don't want to leave.
Because you have to go. Right.
Yeah, so.
So my suggestion would be walk down the street to the bar.
Yeah, it's Italian bar are very, not small, they're very, it's very local.
Okay.
You might like it.
What would they like?
Oh, sure, you invite me.
Yeah.
Yeah, that's it. So you can come to rent. For one. During the talk, I think we do this compromise. We can come for 10 to 20 minutes at all. When I hear people talking for too long, but yeah.
As a plan, right?
Yeah, but as a plan that's worse because you have the blow where the wind, but you don't have the new air. Because it's not just as a plan. You have to just like carbon dioxide. Yeah, just separate the air in interior, but so you have the wind in your neck, but no fresh air.
And we have pure nitrogen. CO2, yeah. Pure nitrogen.
Well, there's a wonderful thing I discovered over by the answer. There's an actual real water bottle. Frozen in ice. This is so American.
But the cooler?
This I have the decency of hiding inside my mouth.
No, I could do that.
So
I might just say, actually,
Would have brought the answer.
well, the thing I like about this, though, if somebody does start to try to
was, but we are here exactly where the lamp is.
You have to install it.
No, we're just showing us how delightful this is.
Yeah, for all the...
So where are we now? No.
Yeah, but you have to normalize by the number of people you need. So, it doesn't make No, I mean, they are doing the classification.
Yes.
No, the database. Just don't, go around with your iPad like that. Also, if you have to use your iPhone, smartphone, don't take it out in the middle of the sun. If you take it out to the street, just move around. People might just come. No, here no. No, it's not on sale. It's just the rest. It's the office area. So all the rest of it are open lunchtime. Maybe the time I'm just.
All right.
No,
I know. I don't.
yeah, so just
That's right. Okay.
just recap what we are doing.
O sea, usualmente, como decía Jorge, tenemos viáticos del interior de Estados Unidos. Pues si vas a Estados Unidos,
Tienes que nadar la costa, no la creas, ¿eh? Eso es pagar el doble, no encontrar la indicación.
I may. Moving to row 1.
¿Vamos a discutir los mismos tópicos o distintos?
Sí, son bastante diferentes. Son coming back.
Ay, ay, ay.
the screen, but I don't know how to use it.
One should be the limit of the other. What actually happens if there?
Okay, better wait for it.
What's this?
Oh, okay. When did that happen?
It's now, so.
Three days.
But you know, if you were to write it as a, say,
Speaking of check,
finite difference
referring a
equation,
letter.
then go back to the continuum
I
limits
just
where you
remind me of referring a
something that is happening continuous, you should get the same thing. After maybe some small discretization, because if you were to instantaneously, as you're integrating in time, every delta t beats as small as you wish. Also, make the star expanding. But when you got the
This was on his page.
10%. How would you define that? How do you normalize it as a total?
You just accept it. Yeah, that's two weeks. I'm happy to discuss if you want.
I see. So it is intended to So obviously there is something else happening there that actually needs some finite time to happen. Because otherwise you don't get the. So can you imagine what it means? There is some other piece of physics there that happens. The confinement would actually mean that the star is feeling larger forces. It's not just the momentum transfer that it's forcing its way through the ground, but I think the pressure actually should also increase the skipping rates. So I don't think it's a pressure that can explain the difference. Okay, yeah, well, I'm wrong about that.
Well, I think that the answer to this is time scale something the envelope, non-linear time scale. So not the calculate every calculates time scale, because of course, really not this is not a time line.
Sure.
You calculate. So it's just the surface that is preserved. So I didn't calculate that. I can feel that it's actually this is but the very fact that we see that
So what? So it seemed that you were getting a much lower collision rate than Pao and Shen got. Can you trace the reason for your result? So what did they do wrong?
So what they were considering is electronics is much larger than in fact the lower density clocks which are large in precision.
I see. So they were too optimistic about the size of the red giant.
And
Yeah, of course. But once you have a
larger red giant, you can make do with the lower density mass, so they have a larger geometric cross section, therefore they have a higher collision rate.
So, that's very much
I'm just interested because you all, apart from that particular aspect, that you were basically assuming a more realistic model for the returns.
also for orders of magnitude surveys of scale.
Well, that's a big difference. Right.
So it's for
But I'm wondering if you were to use, even with your number, just the kind of simple criteria you showed in the beginning, where you basically just look at what fraction of the star lies in the density that is lower than the immediate exponent, and count that part of the use that kind of, simple order of magnitude estimate and compare it to what the simulations give you. How close are they to the rough estimate? It's good for calibrating our belief in order of magnitude estimates.
So we've done that. Haven't seen the results much. I know that they didn't work particularly well. The analytic customers didn't do particularly well
I see. So, sure. You're saying that if you're so close to the edge that you really care about the exact way it falls at the end, then you probably don't make any mistakes. Yes. No, that sounds reasonable, but I wouldn't believe anyway that any model for the outer epsilon percent of the star. But if you assume you have a high enough density to truncate the stars at some deeper level, is it a kind of a reasonable assumption that you say everything is thrown out?
I forgot. I know that we calculate this question basically just calibrate transmutations to calculate that, and I don't remember what I asked for that. But we do that on another platform, analytic estimate, where we look at we basically know what is the fallout of the gas and star company. So we can estimate what is the impact associated with it, the impact of energy associated with that gas. And estimates similar results.
There's I think a pretty dated estimate by, I think it was Sassel and Spitzer in the 1960s, I think, that they were considering the amount of mass loss in stellar collisions. They had something very, also kind of naive, but I don't see that you can really get very different results. They were looking at when you have a collision, so you have some overlap, and then you considered how much of the stellar mass in the collision has escape velocity that is lower than the relative velocity of the star, and you assume that mass gets spread. Then they used it to estimate how many Lansing collisions will the star have to undergo before it's basically destroyed. So on and so forth. There's